Hello, welcome to my virtual blanket fort here at the end of the day where we can just breathe deeply and prove stuff. We're going to prove my Klintberg conjecture today. I have the proof right here in this giant scroll. It's got giant printing, so it ended up being a fairly short proof. But it's got an ingenious key to it that I'm not sure I could have grasped on my own. So let's find out what this is. First of all, what are we proving? Here's my Klintberg conjecture. For every prime p that is greater than 2, so not 2 because there are no primes that are less than 2, p divides 1 less than 2 to the power of p minus 1. And here are some examples. So any prime you like except 2 will divide 1 less than 2 to the power of 1 less than that prime. And 5 divides 15. Oh good, it works. And these others work as well. Fermat's little theorem. This turns out to be exactly the same as my Klintberg conjecture, but better, stronger, more generalized. For every prime p and a in the natural numbers, such that p does not divide a to the power of p is congruent to a in mod p. Well, what does this mean? Mod p. It's a mathy word, it's modulo, but we just call it mod. That means by measure of, from Latin. So this means by measure of p. This is a specific group of numbers, and you can learn more about it in group theory, such that if you divide a number by whatever you put here, so if you divide a number by, in this case, p, you get a certain possibility of remainders. Here are some possible ways that you can think about mod. Clocks or remainders. They both result in the same thing. Here's an example. 16 is congruent to, that's what this means, 4 in mod 12. Here's our classic clock that goes around and ends on 12 and then just keeps wrapping around and around and around. So 13 is the same as 1, 14 is the same as 2, 15 is the same as 3, and our example here, 16 is the same as 4 in mod 12. I'll also point out that in the math world, this 12 should be a 0, because if you divide something by 12, and you get a remainder of 12, you divided wrong. If you get a remainder of 12 and you're dividing by 12, you should get a remainder of 0. So all of these, not these ones on the outside, but 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 are the congruence classes, that's what it's called, of mod 12. Remainders, here's the same example. If we take 16 and divide it by 12, we get 1 with a remainder of 4. So 16 is congruent to 4 in mod 12. Let's go back to this. So these two things look very different. How can we say that they're the same? If we look at this again, we're saying that p evenly divides something, so it's going to have a remainder of 0. We can write this using mod language to say that 1 less than 2 to the power of p minus 1 is congruent to 0 in mod p. Now with mod you can do all kinds of arithmetic with specific rules so that it still works. In this case, we can add 1 to both sides because 1 is definitely less than p. And we can multiply both sides by 2, because 2 is less than p, and p does not divide 2. So we end up with 2 to the power of p is congruent to 2 in mod p. And for Fermat's little theorem, when a is 2, we get the same result. So we did it! The Klintberg conjecture is just a smaller version of Fermat's little theorem, and since this is true, then this is true. Done! Well, that's not very satisfying. We don't get to the heart of why this is true. So let's take a look at the scroll. I have two columns that we can look at. Here are the thoughts that might go towards constructing a proof like this, and then on this side we're writing out the proof itself. So let's take a look. We want to prove this. So first of all, let's just take our parameter and set that up so that that's ready to go. Now let's take a look at this. We want this result. So let's take a look at what can we do with 2 to the power of p. Let's think about this. So we think about it and we think, we have p many of something. What else has p many things? We're dealing with mod. Maybe we should look at some congruence classes. There are p many of the congruence classes in mod p. Maybe that will be useful. You know, if we double all of these congruence classes individually and then multiply them all together, we'll have a factor of 2 to the power of p to work with. So what I'm saying here is we can do 2 times this, and 2 times this, and 2 times this, and 2 times this, 2 times all of them, just double all of the congruence classes, and then if we rearrange all of those factors, then we'll have p many 2's that we multiplied together, so we'll have a factor of 2 to the power of p in that monster result. That might be worth pursuing, but multiplying by 0 won't tell us anything. It's just going to zero out everything. So let's take that out of the plan. So no more 0. Well, that means we don't have p many of this anymore. We have p minus 1. Can we still use it? Well, 2 to the power of p minus 1. We have p minus 1 number of 2's. We could still connect these 2's with these things as long as 2 to the power of p minus 1 is worth pursuing. Well, if we can show that 2 to the power of p minus 1 is congruent to 1 mod p, then we'll still have the proof. Because of what I showed you earlier. Because of this. These two things are the same. So let's execute. Let's do it. Let's do a whole bunch of multiplying stuff together. Here we go. So let's consider, can we see the whole thing? Let's consider that we take a whole bunch of 2's and we multiply them by all of the congruence classes except for 0. That is going to equal, we can just say that we'll rearrange these factors so that 2 times 1 and 2 times 2 and 2 times 3 and so forth, and then 2 times p minus 1 are our factors, so that we're looking at these things. Okay, what can we do with this? Now what? Oh, no, it's okay. We already thought about this last week. This is what we thought about. When we double all of the congruence classes in mod p, we get the same list of congruence classes. Exactly the same list, as long as p is odd. And that's fine, because we already said that we don't want p to be 2 anyway. We said it at the top. So let's take a look at this again. Let's look at these pictures. All kinds of detail here. So again, let's take a look at just this one to start with. This shows all of the congruence classes of mod 5. And what happens when those classes all get doubled? What happens is 1 goes to 2, 2 goes to 4, 3 goes to 6, which is congruent to 1, and 4 goes to 8, which is congruent to 3, and 0 goes to 0. Each of these end up in a different place from each other, but they all are accounted for. It's still the same list, but in a different order. The same thing happens in mod 7, and unexpectedly in mod 9, even though 9 isn't a prime number. It works as long as the mod is in an odd number. When we have an even number, so here's mod 12, what happens? We get some arrowheads that end up in the same place. So for example, let's look at this one right here. 1 doubled is 2, and so is 7. 14 is congruent to 2. This happens in many different places. So this means that when you double all of the congruence classes for mod 12, you don't end up with the same list of congruence classes. So we just want to look at the ones that are odd. Let's take a look just very quickly at a visual representation and a kind of intuitive reasoning behind why odd numbers mean that all of these go to a different place. So, let's say we have a number line and we want to double a particular number. What we do is we can think of there being a mirror right here, and we're just going to flip this distance, starting at 0, over to find our new place. We can think of doing the same thing in this circle arrangement. Let's say that we want to double 1 in mod 7. We can think of there being a mirror perpendicular to the tangent of this circle that slices right in between the 4 and the 5. And the 0, the distance from 0 to that 1, gets flipped over to 2. This happens with all of these. You can check them. And when we have an even mod, what happens, let's take a look at the case of 1 again. When we have that mirror, it slices right through another number on the other side. So this mirror is applicable to not just this number, but this number as well when it flips the 0 over to its new location. So there's just an intuitive reasoning for why do all of the congruence classes end up being the same list of congruence classes when you double all of them. The rest of the proof just falls into place. This part that we just explored is the core of what makes this proof work. Let's do it in the mathy way. Now we're going to consider all of these factors, and then we go through the mathematical reasoning for why all of these doubled gets the same list as just the straight congruence classes. And we're using all of the congruence classes in mod P except for 0 mod P, but that one doesn't interfere because it, when you double it, just goes to 0 again. It doesn't interfere with the list of the rest of them. So we get that all of these doubled congruence classes, when you multiply them together, this product is congruent to just the congruence classes when you multiply them together. Excluding 0 on this side, excluding 0 on this side, we're in mod P, everyone's happy. Now we get that this original thing that we set up here, since it was equal to all of the doubled congruence classes, then it is congruent to just the congruence classes. It was equal to the doubled ones, so it's congruent to just the congruence classes in mod P. Now, using modular arithmetic, we can cancel all of these, and look what we get. 2 to the power of P minus 1 is congruent to 1 in mod P. That's it! That's it! That's what we wanted to prove! Done, done, done. So there you have it. Next week, we're going to explore some binary of some Mersenne numbers. And also on Mondays, I'm doing some music stuff. So tune into that as well if you like. Whichever one you choose, I'll see you next time.